Okay, now it should be working, Henry.
Mhm. Yes, it works.
Okay,
Uh,
great.
I just check question flow. There are totally 267 registered.
That's great. Yep, and I
Mhm.
sent out a
Yes.
reminder, so.
Yes, thank you. Yeah.
Okay, and for those who just joined, thank you. As you hear, we're getting set up here, but we're planning to start at the top of the hour. Thank you.
Mhm. Doing that. Right now, 6 attendees.
It's so quiet.
Yeah. Yes. Mhm. Oh, yeah. Stop sharing.
There you
Yes,
go,
so
Henry.
many. Yeah, 10 attendees.
Yep, it's getting there.
Mhm.
Henry and Samuel, do you want to get started now or do you want to wait a little bit?
Maybe we can start at say they wait for 2 more minutes, like 9:03. What do you think?
I'm good.
Yep,
Yeah.
9:03 then. Yeah. Okay, then we can start now, right?
Yes.
Okay, that's good. Then let me start the opening. Now, good morning, good afternoon, and good evening, everybody. This is Henry Chong, a member of the IEEE IoT Activities Board, and also today's moderator. And on behalf of the board, welcome all of you to join today's webinar. The Internet of Things, IoT in short, is one of the most exciting technological developments in the world today. The key developments or the missions of the board is to promote IoT. Now, currently we have 12 IEEE societies, and we have their total full support. And that's why we have this webinar series. And today is the fifth one, and we are very delighted to have Professor Qing-Shan to deliver an interesting topic entitled Event-Based Reinforcement Learning for Cyber Physical and Energy Systems, Smart Buildings, Smart Grid, and Smart Cities. I'm sure you will all enjoy this webinar. Should you have any questions, do feel free to type your questions in the Q&A box. Now, before the start of the webinar, I would like to introduce Professor Jia. Samuel, you sure the name? Samuel received a BS degree in automation in July 2002 and a PhD degree in control science and engineering in July 2006, both from Tsinghua University, Beijing, China. He is a full professor in the Center for Intelligent and Networked Systems, Department of Automation, Tsinghua University, where he currently serves as the Associate Director. He was the Vice Dean of Tsinghua Global Innovation Exchange Institute from 2016 to 2019, and the Vice Chair of the Department of Automation at Tsinghua University from 2015 to 2018. And he was a postdoc at Harvard University in 2006, a visiting scholar at the Hong Kong University of Science and Technology in 2010, and at the Laboratory for Information and Decision Systems, Massachusetts Institute of Technology in 2013. His research interest is to develop an integrated data-driven statistical and computational approach to find designs and decision-making policies which have simple structures and guarantee good performance. His work relies on strong collaborations with experts in manufacturing systems, energy systems, autonomous systems, and smart cities. And he is currently the executive editor-in-chief of Results in Control and Automation, and an associate editor of Science China Information Science, and he was an AE of IEEE Transactions on Automatic Control from 2015 to 2021. IEEE Control System Letters, IEEE Transactions on Automation Science and Engineering, and Discrete Event Dynamic Systems Theory and Applications. And he served the Discrete Event Systems Technical Committee Chair in IEEE Control Systems Society and the co-chair for Smart Buildings Technical Committee in IEEE Robotics and Automation Society. He is currently the Control for Smart Cities Technical Committee Chair in International Federation of Automatic Control and the Beijing Chapter Chair of IEEE Control Systems Society. He is a member of the 11th Chinese Automation Association Technical Committee on Control Theory and the first Chinese Automation Association Technical Committee on Information Security of Industrial Systems. Very impressive bio. Thank you, Samuel. Thank you very
Thank you,
much. And
Henry.
then I want to pass the time to you. Okay, thank you.
Thank you. Thank you very much, Henry. So I think everyone can see my slides right now.
Not yet. You have to share the screen. Sorry. Oh yes, it's okay now. Samuel, it's fine.
Okay.
Yeah.
All right. Thank you, Henry, for the very detailed introduction. It's been my pleasure to give the talk today and to have some interaction with the audience from the entire world. As you can see, there are two key words in my talk today. One is the cyber physical energy system. Just to give some examples from my perspective, smart buildings, smart grid, and smart cities are examples of the cyber physical energy systems. The second keyword is by methodology, which is a kind of reinforcement learning, but featured by this keyword of event-based. So what are these, and why is it so important to study this problem? To understand this question, we have to look back into the recent history, not very far further in history, but actually many of us has experienced. For example, if you live in China about 5 or 8 years ago, you can personally experience some of the scenarios, which is shown by the photos here. Actually, for some of you who has been spending some time here, you can recognize this is Beijing, this is Shanghai, and the third one is the southern part of China. But these are not fog, these are actually pollution. So as you can see, the global energy crisis and the air pollution has been a dilemma. And is not just a problem for an individual country, but also a problem for the entire world. If you can see, we have a plot here which is showing that the building operation itself consumes more than 40% of the US energy on an annual basis. Right now, this number in China is still less than 20%, but we are rising up sharply and catching up if we don't do anything. On the other hand, there are a big energy saving potential in building operations. And it's not just to save energy, not just to reduce the air pollution. It's actually to reduce the global warming place. So last year, 2021, the Nobel Prize in Physics was awarded to the fantastic work by the scientists in this field to model the Earth's climate, quantifying variability and reliably predicting global warming. So this is actually a global issue. But quantitatively speaking, how much can we actually save if we optimize the operation of these buildings or industries or energy systems? So this is a table. It says that if we don't invent new ways to generate power, but we figured out ways to utilize information so that we can generate more when we need more and generate less when we need less. In this way, we can actually save 2.0% of the energy during the generation process. And for the operation stage, let's say the buildings, if we don't invent new building isolation or building thermal envelope, but we find out ways to sense, to identify those empty regions in the buildings. And we just turn off the lights. We just find out ways to reduce the AC system energy consumption. In that way, we can save 3.0%. We can similarly do optimization for industries, for supply, demand, coordination. So overall, by systems engineering, from optimization perspective, there is 10.5% energy saving potential. And for some of you who are very familiar with the energy generation in China, 70% of the electricity in this country was generated by coal. So when you save 10%, you actually save 350 to 400 million tons of standard coal. That's not just the energy saving, that's actually saving a lot of pollution injected into the environment. Now, we are not just talking about residential buildings. Now, here is a prediction published in the journal Nature about 4 years ago. It was predicted that by 2030, the global ICT will consume more than 20%, that's 1/5 of the entire world annual energy consumption. Among that, data centers will consume 3,000 terawatt hour per year, which is 8% of the world energy consumption. Now, that is about the amount of electricity which is generated by one of the biggest dam in the world. That is so-called the Three Gorges Dam. It's located in the middle of China. And we Chinese people spend 50, 60 years to build one of this dam. And now we have about less than 8 years, and we need to build another 34 just to power up the data centers by 2030. And you have to realize this paper was published before the pandemic. And right now, when still part of this world is still suffering from this pandemic, many of us are just using more of the internet instead of less. So here comes the pressure. How can we save this energy? Well, in data centers, there is an index called the power usage effectiveness, which is just a fraction. It's actually the total energy consumed in the data center divided by the useful part, the part that is used to power up the IT devices. So by definition, this number is, greater than or equal to 1. The closer it gets to 1, it means this data center is more energy efficient. DeepMind is a team. One of its great masterpiece product is the AlphaGo, and Google used DeepMind to power up this operation optimization of their data centers. They managed to reduce this PUE from above 1.2 down to 1.09, and right now it's even less. So there is a huge energy saving potential by doing optimization. It's not just about energy saving. It's actually about what kind of energy you're using. Many giants in this field like Google, Amazon, Facebook, they have been using a lot of those renewable power. So there is a large potential for the rest part of this world to go in the same direction. Now, let's get back to the optimization problem. For example, in China, we have many renewables in the northwest part of the region. We have solar power, we have wind farms, we have hydraulic power, but they are so far away from the power consumption, which is mostly located in the southeast of the country. Now, if we want to match this supply with the demand and formulate this problem in a mathematical way, we can find out this is a so-called NP-hard decision-making problem, meaning it's very hard to solve, and the scale of the problem is huge. There are millions of decision variables as well as constraints. So what should we do? Well, to make the problem even messier, in many of the cases, it's not just a parametric optimization problem, meaning it's not just the parameter you want to optimize or fine-tune. It's actually the control policy. It's actually the scheduling policy. It's a function that you're optimizing. A well-known model in this field is so-called this Markov decision process. And to use the jargon in this field, it means we're looking for a good policy. In order to find this policy, we need to search within the policy space. But this policy space has a huge size. So in order to find this best policy, we need to find something that can satisfy this equation here. There are three greatest challenges. The first one of them is the curse of dimensionality, meaning in many of the cases, the parameters, the variables in our problem can only take discrete values. So for example, if you want to control the air conditioning system in a commercial building, usually the number of the rooms in this building would be proportional to the eventual size of the state space. So if you have 10 rooms, that's 10-dimensional. If you have 100 rooms, that's 100-dimensional. So the total population, the possibilities for the states will just rise up exponentially with respect to the size of the problem. We call that the curse of dimensionality. So how do we address that? The second challenge comes from the multi-scale, because sometimes you need to match the supply with the demand, and they're generated in very different geographic locations. And I can have this prediction model on an hour basis, on a minute basis, on a second basis. They're at different spatial temporal scales. How do I utilize those different models in the same time? That's the second challenge. The last but not the least is the uncertainty. Renewables are good, but renewables are, in many cases, are very random. How are we going to match this uncertain supply with the uncertain demand? That's the third challenge. How? Well, the easy answer is artificial intelligence. It seems to be the buzzword right now for many questions, if not for all. But really, what is AI and what are these AI methods in my talk? I would say, first, the great technology of IoT just make the sensors to be so small, teeny tiny, so that we can actually put that into many devices to collect data. And then we have a huge amount of data. That's the big data. The data, when it's become big, it's good, but sometimes the density of the information just becomes less. So it's hard to actually find out the useful piece of information from a huge amount of data. In order to do that, you need the cloud computing. Cloud computing sometimes has different names: ubiquitous computing and pervasive computing. It actually shares something in common. It means computing as a service has become so easy to access. Actually, right now, if you have a smartphone which connects to the internet, you can actually rent just, a cloud or just a computer in the. So when you have this IoT, the big data and the cloud computing, the key challenge is how do you actually do decision making? Now, I will try to minimize the amount of mathematics in my talk, but this one is actually very good. So this is a classical model for Markov decision process. It means in the beginning, you have a state. Let's say in a temperature control problem, the air temperature in the room is your state. So you have different actions to take. You can turn on the AC to cool down the room. Then suddenly you need to pay for the bill, right? And because the AC is working, after a while, the air temperature in the room will just reduce. So you reach another state S1 and you can take some other actions. But you can also shut down the AC and just open the window so that you use natural ventilation to cool down the room. It may be slower, but definitely much cheaper. So different action leads to different next stage. And then you have a different cost. Sometimes this state transition follow a probability distribution. So you have a one-step transition probability. Now, in this model, the decision making is to decide your current action when you have all the historical information. Now remember, it's all the historical information. But do we actually need all the historical information? The Markovian property says, if your system has certain kind of nice feature so that I don't have to remember your history, I only need your current state. And once I have the current state, the future becomes independent from your history. So if your system is so nice, then I can remove the historical actions sequence and your state sequence. I can just use your current state to make the decision. Well, this is great. It simplifies the problem a lot, but not enough. Because even if you can do that, there is still this curse of dimensionality, this uncertainty, this multi-scale problems that's haunting you. So I would say, why don't we use event to trigger our decision making? So what is an event? Mathematically speaking, an event is just a set of state transition pairs that share something in common. For example, in the temperature control problem, we can define two types of events. The hot event, meaning your room temperature just rise from some value below a threshold to some value above the threshold. Let's say above 26 Celsius degree, that's a hot. And you can have a second type of event, which is cold, meaning your room temperature just drop from, let's say, above 18 Celsius degree to beneath 18 Celsius degree. That's cold. Then using hot and cold, only two types of events, you capture the key changes in the system dynamic. So we can see events can be used to aggregate system states. If you define events appropriately, then the number of the events can increase linearly or even stay as a constant. While in the same time, the system state space will just explode exponentially fast. But clearly, event does not equal to states. So mathematically speaking, event-based decision-making is essentially a partially observable MDP. Therefore, we need event-based reinforcement learning to solve this problem, either exactly or approximately. How? Now, as we can see, I'm trying to use one slide to compare non-reinforcement learning versus reinforcement learning. So on the left-hand side, this is Monte Carlo. It says, okay, I don't know, should I turn on the AC right now? Then I just run simulation. So my current room temperature is marked by this red dot. And I know people are coming in and getting out, so I run a simulation to get a sample pass. I know there are randomness, so one sample pass is not enough. I just do this multiple times, and then I use the sample average to tell me what is the consequence for me to turn on the AC when the current event is hot. And I can do similar analysis for the other actions. Let's say, why don't we just turn off the AC and use natural ventilation? So you have this prediction for both actions. Compare them, you find out which action is better. That's Monte Carlo. That's great. That's actually embedded in many commercial software right now. What's wrong with it? Nothing wrong. It's just because, we need a simulation model to use this. And simulation models are built by experts, let's say experts like me. And it took us a while to build a model. And as time goes by, the model deviates from reality. We need to recommission the model. It takes some other time. And we need to do this, from time to time. It's not very convenient. How about we look at this single sample pass? And then we find out in this single sample pass, the same state, the same event actually occurs by multiple times. Let's say, for example, this red dot, it occurred twice. What if we just cut off the sample pass and then just treat it as if they were generated from two independent simulations? That's great, right? And we actually can do this for all the other states. Let's say this blue states, yellow states, green states. We can do this for every state that occurred so far. The beauty of this is we actually can use the historical sample path to predict the consequences for taking a particular action when certain event occurs. So if you have a long but a very long history stored, it can tell you a lot. It can help you to make the right decision for the current state. That's the key idea of reinforcement learning. We give it a name called temporal difference methods. Why is it so beautiful? Because I don't need simulation model. All I need is data. And data can be acquired by sensors, cheap sensors, relentless sensors. They don't feel tiredness. They don't sleep. I mean, they're, sleep by, because of the battery, but no, they're much cheaper and much, much, much better and more convenient than experts. That's why reinforcement learning methodology has become so pervasive in engineering fields. Now, in the last few years, there is a combination between deep learning and reinforcement learning. What's the fuss about that? Well, many of you can recognize these are the posters for the Avenger game. And in the Avenger game, there is this Doctor Strange. He has a special capability. He can walk in different multi-universe. Why is that so important? Because when we are facing engineering problems, when we are asking what-if questions, in many of the cases, no matter how long you have recalled your history, it's just a so teeny tiny fraction among all the possible histories. So we need a way to predict the consequence of my actions in those states which has never occurred before. And in order to do that, we need some generalizable functions. That's where deep learning enters the picture. So as you can see, you can use deep learning to predict the consequence for certain actions at certain states or events, even though this event-action pair may never occurred before, but it's fine because I can predict. Okay, so that's the key idea behind it. Now, I'm just trying to solve the three challenges one by one. The first challenge is the curse of dimensionality. Many of you would say, is it so difficult? I mean, the curse of dimensionality? Maybe not. Actually, in reality, there are two main ideas to address it. The first one is complexity. That's the point. And then we face policy, and you realize this policy is so complicated. There is another methodology which says, let's forget about the performance. Let's focus on policy. Let's threshold policy. But when you get best among this threshold type of policy, you might realize these policies are not good enough. So what should I do? Can I just quantify this complexity of a function? And this is actually a long-standing problem. Many mathematicians have worked in the field. As you can see, Kolmogorov has defined this descriptive complexity. And then he also shows that in order to calculate this specific value for Kolmogorov complexity of any given, let's say, function, this problem is mathematically equivalent to the halting problem of a Turing machine. And we know that problem is incomputable in general. Incomputable means it's even harder than any. Okay, so what should we do? Well, in engineering problems, there are usually some nice property and features. For example, many temperature control problems in our data centers do share structure like threshold type. And if we use hot and cold event to define event-based policy, we realize these policies actually provide good approximation for many control laws. And if we define the events properly, the number of events can stay even as a constant, no matter how many rooms you have, no matter how large this data center is. And that is very beautiful. Now, by using the ordinal optimization, we actually can convert the original problem, which is calculate the complexity of a policy, which is, when you do that for sure, is incomputable in general. We can convert this left-hand side of problem to the right-hand side. This is actually two objective functions. The first one is complexity. The second one is performance. And we want to find a Pareto optimal for this problem with high probability. So that's a typical formulation from the jargon of vector ordinal optimization. So what is that? All right. So this is a very basic idea of ordinal comparison. The first one, these are two hamburgers. I'm asking you, which one is bigger? Well, many of us will say the right-hand side is bigger. But if I ask you, how much bigger? Let's say in the unit of centimeters or millimeters, that's a much harder question. Why? Well, because it's easier to find out which design is better, which solution candidate is better, than to answer how much better. And the second idea, these are two dashboards. If you take my class in Tsinghua University, I give you this opportunity. Why don't we give you 4 dash? And you can pick one from these two dashboards and throw your darts on it. Your score would be the final score of your course. Which one would you pick? Many of our students would pick the right-hand side. Why? Because it's bigger. So it's easier to hit. What does that mean? That means in our optimization problem, it is much easier to find a good enough design than to find the optimal design. So ordinal optimization actually utilize these two basic ideas, ordinal comparison and Gauss-Softening, to reduce the significant magnitude, usually at least one order of magnitude. So I can use a crude model to find the good enough with high probability. I'm just using the similar idea, but for two objective function case. All right, even further, I can utilize a sequential computing budget allocation way so that I can estimate the trade-off between the complexity and the performance of my control policy. Now, this shares the idea with the so-called optimal computing budget allocation. It was first developed by Professor Qing-Shan from George Mason University in the United States, and you can find many technical details in this great textbook by Chen and Lee. Now, first idea, and we just successfully apply this idea to the operation optimization of internet data centers. We can reduce the energy consumption, and we can even predict the remaining lifetime of certain devices, let's say the batteries. Now, the second challenge, multi-scale. Now, let's say I live in Beijing. So I drive electric vehicles to work. Does this mean I'm helping this air pollution saving problem? Not necessarily. It depends on what type of energy that is used to charge my car. If I'm using this electricity from the state grid, then you're not reducing the CO2 emission. You simply change the geographic location. You change where the CO2 emission occurred. You don't reduce it. But if I use renewable power, let's say the power generated from high-rise building by wind, then this is green power. And you use that to charge your electric vehicle. This is reducing CO2 emission. But am I dreaming? Let's use data to discuss. So in Beijing, there are 6 rings. Beijing is a big city. Even if we focus on the 4th rings, within that, there are more than 900 buildings which are taller than 50 meters. There are more than 300 buildings which are taller than 100 meters. If I deploy wind turbines on top of those high-rise buildings to generate power on an annual basis, the amount of power that has been generated by these wind turbines, so-called mounted on the high-rise building, would be sufficient to support more than 50,000 electric vehicles for the entire year. Now, that's a huge amount of power, but this claim is based on a big assumption. That is, you have a big battery. If I don't have this big battery, is it still a positive claim? Turns out to be yes, but this is a challenging problem because electricity is very special. You have to match the supply and the demand anytime. So for a single stage, on the left-hand side, you have the power generated from the wind, which is usually free, but very random. And you have the power generated from the day-ahead market, relatively cheap. You have the power generated from the real-time market, which is expensive. On your right-hand side, you have the power consumed by many thousands, but in our study, we focus on the electric vehicles. Now, you have to make sure the left-hand side and the right-hand side, they match with each other. And don't forget, wind power generation and the EV charging demand, they're random. Now, on a daily basis, on the right-hand side, you have the generation curve from 3 different resources. The wind, relatively cheap, but very random. From the day-ahead market, relatively cheap. Or from the real-time market. Well, that's, very expensive. On the left-hand side, you have the charging demand from a single EV, from many EVs, and they don't just charge once in a day. They probably could be charged for more than once. Okay, so these 2 curves should match with each other. And even worse, this wind power generation, they're so random. And my charging demand depend on my human behavior, which is very hard to predict. And one day ago, the electricity price is cheap, but I don't have the perfect prediction of my demand. One day later, I have the perfect information, but the electricity price just rise up. So it seems that I need to make a decision. I need to buy some amount of electricity one day ahead, not too much, not too less, and I still need to buy some rest power in the real-time market. So the question is, how much should I buy from both markets? Well, this problem is challenging. The basic idea is I have to match the wind supply by aggregate the total amount of power to charge the electric vehicle. And then I distribute that amount among the many electric vehicles. This problem can be solved in two different time scales. When in the day-ahead market, you have plenty of time to use a complicated stochastic model. That is fine. The other one is in real time. You don't have time to do a very time-consuming calculation. I can only use a simplified model, even use a deterministic model to approximate it, but I can do in rolling horizon to continuously use new sensing data to, refine my model. But I have to use this deterministic model to speed up my calculation. And I have to utilize some feature in the problem because the number of electric vehicles, when it increases, the total combination for the charging action will just increase exponentially fast. If you have a single car, it's only 2 actions to charge or not. If you have 10 cars, you have 2 to the power of 10. That's over 1,000 action candidates. If you have 1 million cars, then every time when you make a decision, you need to compare 2 to the power of 1 million action candidates. That's just impossible. But we find out there are some nice features. You can actually rank all the cars according to how urgent they are. For example, if this car is just recently parked here and it will be parked here for overnight, then I will say it's not very urgent to charge this particular car. On the other extreme case, if this car has been parked here for a long time and is about to leave, and the battery is still, almost empty, then I have to put this car in this very urgent label so that I can charge it first. So using this urgency index, we can rank all the cars. But after this ranking, your decision is no longer which particular car to charge. Your decision is how many cars to charge. And then I just convert that according to the urgency index from the most urgent one to the least urgent one. So I reducing the action space from exponential down to linear. Now I just use this idea combined with reinforcement learning to solve this real problem. We find out when we utilize the model from both time scales, the optimization can not only reduce the overall cost, but actually utilize much more renewable power than otherwise. And the similar idea can be extended to incorporate solar power and when you have better understanding of the wind power generation. This is not just a single problem in engineering. It actually shared the feature across many engineering fields. In many of the cases, we have a simulation model from different scale. I have low resolution simulation model, which is very fast to run, but their prediction is so crude. I can also have this high resolution simulation model. There are many very accurate, but they are also very, very slow. So what should I do? Which one should I pick? Well, this is not just for engineering faculty study. If we go back in time, in 2013, the Nobel Prize in Chemistry awarded to 3 great scientists in the field for their development of multi-scale models for complex chemical systems. So, getting back to our question, we utilize events to connect the models at different scale. So from downscale to upscale, from micro to meso, from meso to macro, we can use aggregation of the states, aggregation of the actions which are captured by the events. And from the other direction, from macro to meso and from meso to micro, we can use projection. So use this idea, we don't need to pick models. We just use all the models we have. So this idea has been implemented in the Northwest grid in China. We can effectively simulate the power network incorporated over 7,000 nodes and multiple energy resources for optimization purpose. The last challenge, uncertainty. Well, you may not realize we are very uncertain as human beings. The UN IPCC, Intergovernmental Panel on Climate Change, actually published a report. It says the human behavior may affect the energy consumption in buildings not like by 10% or 20%. It's actually up to 10 times. So there is a big difference between the timetable simulation and the ground truth. So it's very important to get the ground truth. How do we get it? First, we need to utilize the human-building interaction. The traditional thermostat is not smart enough. For example, I don't know, is 26 Celsius degree the best for me? Why not 25? Why not 28? I don't know. So we developed this Qing-Shan human-machine interface, which allow people to complain. I don't know why I'm not comfortable. I'm just not comfortable. So are you feeling too hot, too cold, too dry or something? So you can just input into this HMI. Then together with the sensors we deployed in the room across the building, we can learn what kind of thermal comfort model you are for each and every individuals. So we implement this idea in the low energy demo building on Tsinghua campus. And we actually solved two optimization problems. One problem to utilize all the terminal devices for energy efficiency. The other one to cooperate all the energy supply systems. So the two problems were just iterate for the overall efficiency and comfort. We call that the I building because when the occupant has some dissatisfaction, he or she will just let this building know through the HMI. And when these different complaints are received, we pass that into an interpreter. Then this will be interpreted into different set points, which then will in turn be passed on to the controller to control different devices to alter this indoor environment. Now, hopefully the occupant will feel much better. Now we call that closed loop. So there is something further here. The building structure has some nice feature. Many rooms are very similar to each other. So we can actually use this decoupling to speed up the simulation. And also, we as a human being, our behavior have statistical features. So we can utilize the state-time statistical model to improve the estimation accuracy on the occupancy level. So for example, if this is a, let's say, this is a corridor, and our sensors are telling me that there is a people standing in the corridor for 1 hour, let's say, this is unusual. I mean, this is still possible, but not very alike. So I would just say this probably is not a real human being. It's probably a sensing error. Okay, that's the basic idea. So we apply this methodology in quite a few buildings, not just in Tsinghua, but also in many different places, and found out that this could improve our overall building operation efficiency. And we can incorporate our statistical model with the other sensing techniques to further improve their accuracy. So in conclusion, cyber physical energy system merge the information flow and the energy flow to achieve safe and energy efficient scheduling. Event-based learning and optimization can address large-scale distributed decision-making problems. But this is not the end. The best is yet to be. We are not alone in this field. As Henry mentioned earlier in the beginning of this talk, we have quite a few technical committees in Control Systems Society, in Robotics and Automation Society, and in International Federation of Automatic Control. And we regularly organize a workshop and special issues. And many of the technical details in my talk can be found in these books. And I will use 3 more minutes to talk about some ongoing work. First of all, when we use CPES, Cyber Physical Energy System, to connect the data centers, why don't we just move the data instead of moving the energy? Because moving the data, you just require the fiber, right? Which is much easier than just moving the electricity. For moving electricity, you need ultra high voltage power grid. But for moving the data, you just need a fiber, which is very cheap. So that's actually last year, China announced its national strategic initiative to use the renewable in the west part of the country to support the data centers across the nation. But realize that when you move the data so frequently, that means your supply-demand topology will change very frequently. Can our existing infrastructure support that new and very frequent topological change? That is a question. Second, when we mention reinforcement learning methodology, we assume the system can learn. But really, what's the cost? In many cases, when you have autonomous car learning on the road, ideally, this car won't hit anything during the learning process. But this is, very hard for the current technology. So can we develop reinforcement learning technology which can guarantee certain safety critical constraints all the time? Can we? If we can, that's a great leap for the current control laws. Last but not the least, we have talked a lot about energy saving. But how about we just change the energy consumption model for computing? I mean, this is a human brain, right? Everybody, we got a human brain here. Human brain is, in many perspectives, much, much slower than computer in many tasks, but also much, much more energy efficient than digital computers. What can we learn from this? Can we utilize other ways for the computing, but more energy efficient? I think it is possible, all right? It is possible. So, thank you very much for giving me this opportunity to share with you my thoughts and the work of my team in this field. And this is a two-dimensional QR bar of the WeChat system of my lab. So if you have the opportunity, I welcome you to visit physically or over the internet. Thank you, Henry, and thank you, everyone.
Okay, thank you, Samuel, for delivering an inspiring talk. Then the talks cover different aspects from energy generation and utilization, buildings, infrastructure, as well as optimization techniques and the use of AIs in those areas. And most importantly, the use of AI in coordinating all these areas. Very inspiring. Thank you very much, Samuel. Thank you. Now,
Thank you, Harry.
it's a Q&A session. Do you all have any questions?
Yes, I can see
Please.
there are three
Yeah, there's a
questions.
yes, please. Yeah.
So the first question is, we're most likely all electrical engineers. So as a structural engineer, you evaluated the impact of a wind turbines additional loading on a building structure, the effects of putting a wind turbine on top of a tall building. So it's a good question. Yes.
Yeah,
So I'm
exactly.
not just I'm not just saying that I just climb on top of the building and mount a turbine on it. So no, you have to utilize a special type of wind turbine. By the way, I don't have any business with the picture I showed in my slides. I'm just to say my point is, you don't need to invent new wind turbine. There are existing technology. You can just purchase that from the market. And I believe when you purchase that, it comes with a menu. Okay, they will tell you for the particular building you're intending to mount, what type of specific device is recommended. So, technical response to a question, you need to consider the perspective of the wind turbine would cause vibrations actually to the building. If this wind turbine is gigantic in size, then it is not recommended, especially to places when there could be a frequent change of the wind velocity. For example, in the city of Beijing, sometimes in the transition season, there could be dramatic change of the wind velocity on a minute basis. Then it is recommended to use small wind turbines. You could have several one of that instead of a gigantic single one wind turbine. The second question is how the scalability and efficiency can be balanced along the security aspects in the smart buildings. Okay, so scalability and efficiency in smart buildings. For my talk, I focus more on the trade-off between the comfort and the energy efficiency. If you're talking about that, and if we're talking about smart building, then we actually need to consider some other perspective at the same time. One particular issue is privacy, and it comes with different culture background and preferences. For example, Asian people where I live have less concern in privacy comparing to the Western people. So we could live in a very highly, I would say, highly dense buildings, high rise, which is less likely in the Western part of the world. Now, scalability, when you have a high density in the building, for example, high rise building, it's actually good for energy efficiency, but not very good for comfortable and not very good for privacy. For other perspectives, for example, if you are connecting the buildings in a small region, let's say a community, multiple buildings in the same community are connected with each other, then you have to consider the energy supplies for each single one of the buildings. It would be better to have a diversified asset. So some buildings have solar panels, some buildings have, I don't know, geothermal, some buildings have, let's say, wind turbines. Then it will be much better to connect these different type of buildings in a microgrid, so that this randomness in the different energy resources intend to be independent from each other. So we know there is a law of large numbers. So when you have randomness in wind, in solar, as well as in other resources, but if you have multiple resources to supply your energy in the same time, the combination of those things intend to be less random, which means more reliable, which is good for the small community, the small microgrid. So that's my relatively long answer to this question. The third one is, many thanks for the description of control models using RL. Question for ongoing activities. Can we move only the model encoded the hyperparameters of the data instead of the energy? By the way, different locations, can we say it could increase the trustworthiness of the controllers? Very good question, actually. It actually related to the cybersecurity. When we talk about this particular question, actually the reinforcement learning based control laws are not the first choice. So when we utilize the hyperparameters, we also want the model to be explainable in the sense that it's not just a parameter which guarantee the controller has a good performance, it's also the structure of the controller that give us some guarantee or confidence in the performance output of the controller. So that means when we design a controller, we want the controller to have nice structure, number one, and also second, nice and well-tuned hyperparameters. So when your controller was designed in this way, you can easily transfer the structure of the controller from one place to another. But for the hyperparameters, you usually need to retrain that using the other data in the new location. So that's my answer to the third question.
Okay, very good. Do you have further question? Samuel, I have a question regarding the energy. About the CO2 emission, what you mentioned at the very beginning. Everywhere is now promoting electric vehicles, right? EV
Yes.
things. However, some people have commented that the use of electric vehicles is just to aggregate all carbon dioxide emission from power plants, okay, power companies. Or in short, energy conversion and energy emission is done, but not on vehicles, but power companies. Now, at the same time, the retired EV batteries will sooner or later become a problem. Then, what do you think about this?
This is a very good question, and as part of my talk has also mentioned, yes, the battery is a issue, and it would be nice to have better batteries than the current ones. So there are some existing research going on in my lab trying to study the alternative type of batteries, which can provide sufficient power to drive the car, but less pollution and
Exactly.
hopefully recyclable. So I guess that would be a perfect answer to your question. But you know, I believe we are not alone. There are many other research groups in this world are having the same objective. So if we are using the current battery, then what you described is true and is actually a issue, a major issue. Not right now, but about 5 or 10 years later,
Yeah,
that will
exactly.
be a significant and critical issue.
Yeah, that's what why we are here, because we keep doing the research how to use.
Yes,
Yeah.
yes, that's right.
Yeah.
Yeah.
Now, in a question about AI, okay, many people have a comment on using AI. Once we have used AI in solving problems, scientists or technologists have no way to understand the problems in detail. It's just a black box, as what you mentioned. We don't need models. We can only see the inputs and outputs or expected results, and we don't know why. conversely, scientists or engineers sometimes want to know the model. Then what do you think about this?
Oh, I definitely agree on the models. I would say that the models help us to explain things
Yes,
and
exactly.
help us to understand things.
Mhm.
And that's why we do research, because we try to understand things. All right.
Mhm.
So personally, I think the current combination between the models and the data is because the previous models, many of the previous models are not detailed enough.
Mm, mm, mm.
And some of the reason is we previously don't have enough sensing data to purify the model, to detailize the model. But now we do.
Mhm.
But on the other hand, in many of the cases, the engineering problem has become so complicated, so complex, in a sense, it actually touch upon the basis of a different discipline. Okay, so if you want to describe a car, let's say autonomous driving, if you want to use a detailed model to capture the electric car, it actually not just the electricity, it's actually mechanical engineering, electrical engineering. You have many engineers to figure out the models for a single car. And in those cases, we need a way to combine those models. That's why we need data, because there are so many different ways to fine-tune the parameters that connects different models. And the data, in some cases, is the best way to tell which particular combination make more sense. So my interpretation between this relationship between model and data is not they are conflicting with each other, but on the other hand, I would actually say they will help each other. So I would recommend to utilize the data and the model to improve one another. When we have more data, we can build better models to explain the data. And then once we have this better model, then we can just make a better prediction on what kind of data we have. And then we have new data. We just have to figure it out if that new data is consistent with our refined model or not. So this way, we help to ourselves to understand the issue.
Yes, yeah. In the university, we do see many students when they do a like a final year projects, for example, they just use a standard AI toolbox, for example, to deal with some problems and fit a lot of data, and they say, oh, it is high tech. But in fact, they know nothing about it and no domain knowledge. And as what you say is important, it needs necessary to strike a balance, like the models, the domain knowledge, and the use of AIs and the use of data. And I totally agree with this. Yeah,
Yeah,
this.
right.
Yeah, totally agree with it.
Yeah.
Okay, do you have any further question you would like to ask Samuel? It's very inspiring. I enjoy it very much. Yeah, thank you very much, Samuel. Yeah.
Oh, and I also have my email right here.
Yes, you have any questions, I'm sure Sam is happy to answer of you.
Yeah.
Okay. Then if you further question, thank you very much. Time flies. We have come to the end of today's event. On behalf of the IEEE IoT Activities Board again, I would like to thank Samuel for delivering such an informative and insightful talk. And thank you very much for attending today's webinar. And we will upload today's presentation onto the IEEE Resource Center and also our YouTube channel. Then you can enjoy Samuel's presentation again and hope to see you again. We will soon send you information about the next webinar. Thank you for joining. Goodbye. Have a nice day and evening. Thank you very much. Thank you, Samuel. Thank you, Karen, for helping
Thank you,
us.
Karen.
Yeah, and
Thank you.
thank you both so much on behalf of IEEE. Really appreciate all the time and effort you put in. And for everybody that participated, thank you so much.
Thank you very much.
Great
Thank you very much.
day.
Yeah, good
Thank
day.
you. My
Oh,
pleasure.
my
Good
pleasure.
day.
Oh, bye.
Bye.
I just realized I forget to turn on the video. Sorry. Thank you very much.
Okay. All right. Thank
Bye.
you. Honestly, that was a great talk.
Yeah.
Thank you. Thank you.
Bye.
All right.
Bye-bye.
Take care. Go to
Bye-bye.
sleep. Have a good evening.
Okay.
Bye.
All right. Have a good day.
Bye-bye.
Bye.